We're speeding into the fast lane with Globe's 5G technology. It's fast, it's fun, it's wonderful. It's Kim Son-ho approved. With Globe 5G technology, the possibilities are endless. It's about time we inspire the youth to create something meaningful, spark reinventions, and improve the framework of the future. That's what the 5G hackathon is about. Students, professionals, and startups are welcome to join the event by registering using this link. Once accepted, you may enjoy access to the Globe 5G Hackathon HQ, where the enablement workshops will happen. That's 2 weeks worth of fun workshops and mentorship by industry experts from our tech partners. All these to get you to the top. That doesn't end there. Apply what you've learned from the workshops and pitch your idea on how you can use 5G to improve the way we live. The panel will pick the top 30 semi-finalists to join the pitch competition and enjoy exclusive workshops and consultations with mentors. But if you're truly, madly, deeply at the top of your game, you can be chosen as part of the top 10 finalists who will proceed to the Hackathon Finals. 3 of the best pitches will be hailed as winners. What's in it for you? Well, over 500,000 pesos worth of prizes will be given away, plus a chance to be part of the Venture Builders program of 917's Venture Velocity and work directly with Globe 5G Acceleration Lab. This is powered by Globe and Automl Labs by DLSU. Thanks to 5G, we're about to achieve great heights. Click the link and show us what you've got. Get ready to reinvent your power to create change. Register now.
Do you wanna make a difference and reinvent your world? 네, 안녕하세요. 여러분, 김선호입니다. 샌드박스 같은 곳에서 경쟁하는 기분을 느껴보고 싶으신가요? 그렇다면 글로브 5G 해카톤에서 진행하는 워크숍과 멘토십을 통해 5G 활용 방법을 만들어보고 여러분의 친구, 동료들과 팀을 만들어서 디지털 시대 속 필리핀의 새롭고 흥미로운 가능성을 열어보세요. Follow your dream. Register now.
You watch me do my thing. Reinvent the world, yeah. Just to be more, just to be better, just to evolve, just to be more, just to be better, just to evolve, just to evolve. Every time the world spins round, reinvent 360. Thinking you gon' miss a good thing, yeah. And show the whole world. Reinvent, nobody should know something. Be strong, be a good friend. You watch me do my thing.
Take it to the next level with Globe's fiber, LTE advanced, and 5G mobile connection. Now you have the power to reinvent your world. Globe.
The new mind-blowing Surfer 99?
9 gig? All sites?
For all devices?
Shareable with up to 4 people?
Like my fam? Anywhere they are?
mind-blowing Surfer All 99.
Dear Mother, light of the home.
Dad.
Hey, baby!
Greetings, Professor Rodolfo.
May I be absolved from
Math club tomorrow.
May Globe Virtual Hangouts kasi.
Go and hang out from wherever you are. Just open the Globe One app, choose an event, and click join.
Watch concerts online!
Dance together.
We can do quiz nights.
Yo, let's go! If you allow me,
I promise.
To make it up to you.
And repay your kindness tenfold? Truly, your favorite child.
I love you, Dad.
please, babe.
Thank you, sir.
Enjoy your fave events with Globe Prepaid Virtual Hangouts. All together now.
Yes.
Get it? Get it? Yeah. Get it?
Welcome to this session on multi-access edge computing and related use cases. Before we talk about edge, it is important to understand the differences between 4G and 5G. While 4G focused on broadband internet, 5G brings a paradigm shift by creating the foundation for an entirely new generation of innovative services. This foundation is needed to support the dramatic growth of mobile users, demanding more and faster delivery of data services, and also because of the proliferation of Internet of Things devices. In addition to this, emerging services around augmented reality, the use of drones, and futuristic ideas like autonomous driving cars, which are now very close to reality, impose new requirements on communication technologies. In response to the pressures of these demands, the International Telecommunications Union, ITU, crafted the IMT 2020 standard, commonly referred to as 5G, to address three key mobile markets, each with unique requirements. The first market, referred to as extreme mobile broadband, is primarily concerned with communication services for human-centric use cases that allow users to access increased broadband speeds via mobile services. 5G's second market sector, formerly known as massive machine-to-machine communication, serves what has come to be known as IoT. In this role, 5G is expected to provide the wireless web that ties together large numbers of connected devices, perhaps in the millions or tens of millions, each transmitting a relatively low volume of data. Devices that support these applications are required to be low cost and operate for many years on small battery pack, which means you need to optimize the way you communicate across the wireless communications network. Finally, the critical machines communication segment serves machine-to-machine applications where ultra-reliable and low-latency communication is compulsory. Examples include vehicle-to-vehicle communication for autonomous or semi-autonomous vehicles, wireless control of industrial manufacturing and production processes, remote medical surgery, smart transportation, and other safety services. This is an area where edge will play a very, very important role. 5G is not just about connectivity, it's actually about business outcomes. Now, as we talk about building next generation consumer and enterprise services on top of 5G technologies, it must be understood that 5G connectivity is only one part of the puzzle. There are a number of other pieces to the puzzle that include technology elements like edge and cloud, and also focus on building ecosystems and vertical solutions. So, Gartner, for example, looks at successful 5G deployments as those that combine the 5G connectivity technology with business platforms on which very specific Industry 4.0 solutions can be built, or, for example, on which next generation communication services can be built that are centered around smart homes, smart lifestyle, health, and so on and so forth. When we look at some of the markets where 5G has been deployed early, it is clear that being successful with 5G requires both stimulating consumer interest as well as catering to enterprise needs. When we talk about the consumer, I think the key thing that we see is that in addition to enhanced connectivity, creating immersive experiences with differentiated content, both in personal spaces like homes as well as in large events, is extremely important. This means that there needs to be a lot of focus around creating lifestyle services, especially those focused around sports and esports, gaming, entertainment, education, and other forms of virtual communication. In addition to this, the way some of these content is required to be delivered is also changing. There is a lot of demand for virtual and augmented reality content, and also, for example, for cloud gaming. Many of these require edge as a key underlying infrastructure to really build and deliver these next generation services. So, how do you build some of these next generation 5G services? The way we see it is that it requires not just 5G connectivity, but the use of edge technologies, as we will shortly see. In addition to this, this also means bringing the cloud closer to the edge. And this could, for example, be in the form of AI and machine learning services that would run on the edge, or this could be in the form of other general purpose network and storage capabilities required to be set up at the edge to deliver some of these services. Let's talk about some of the next generation services that would get enabled by 5G. Let's start with a consumer perspective, then we'll shift to an enterprise perspective. From a consumer standpoint, this is a Ericsson Consumer Insights report finding from 2019 that's still relevant today, where it lists out and categorizes a number of consumer use cases across 6 or 7 broad categories. Some of these are existing services that would benefit from augmentation through the use of 5G technology. Others are completely new services that can only be delivered with 5G. Enhanced mobile broadband, the category in green, is a good example of an existing 4G service which is augmented by 5G, essentially to deliver mobile broadband experiences with speeds in the order of gigabytes per second. But if you look at some of the other use cases in gaming, AR, VR, entertainment, smart homes, smart shopping, there are completely new services that can be created and that consumers expect to be created as part of 5G rollouts. A good example is VR cloud gaming. This is a use case that is extremely latency sensitive because in order to deliver optimal game experiences, you need to have latencies less than 15 or 10 milliseconds. This means the way the service gets built and delivered is going to be fundamentally different from the way you deliver cloud gaming today. And this is an area where edge infrastructure will play a very, very important role. We will talk about some of the specifics around how edge infrastructure reduce latency in a couple of minutes. But this is a key takeaway that edge is going to be fundamental to deliver low latency services in many, many different use cases for both consumer and enterprise. When it comes to building 5G services for enterprises and industry verticals, there's a lot of potential use cases. There's a lot of opportunity for innovation. Now, many of these use cases across industry verticals need core horizontal capabilities. One such technology and horizontal capability that is needed is AI and machine learning at the edge. We now have the ability to build and train large complex AI machine learning algorithms on public cloud and then export those models to be deployed on the edge in different devices of varying form factors. And this can be used to drive machine learning and AI based applications that involve processing of speech, vision, video, as well as massive real time data feeds. And this is important for different industry verticals like retail, healthcare, manufacturing, logistics, and automotive telematics. So let's define edge computing in much more concrete terms. It essentially is related to moving computing capabilities and applications that use those computing capabilities towards the edge of the network, closer to where the human user or the device consumes the service delivered by the application. The whole point to do this is either to optimize the experience and enable low latency applications to be delivered, or in many cases, change the economics of the overall implementation. In some cases, for example, processing of data by bringing it all the way to the public cloud may not be economically feasible. In many cases, you could offset that by implementing processing of data locally so that then the costs of transporting that data all the way to the public cloud is not there anymore. So it completely changes the economics of implementation. Now, from an overall market standpoint, the edge computing technology is going to be vital in terms of creating new revenue streams for telcos. And in many ways, the importance of edge in a 5G context can be correlated to the importance of over the top applications in a 4G context. This is where value creation in the overall value chain is likely to happen, and edge computing is a core underlying foundational technology to drive that value creation. This interesting analysis by KPMG shows that the connectivity part of 5G would account for a smaller fraction of the overall addressable revenue opened up through the potential of 5G and edge computing in terms of applications and services built on top of it. And this is one of the reasons why, in order to really capture the potential of 5G and edge, telcos need to find ways to elevate their role in the overall value chain. Let's talk about how edge fits within the telecommunications network. I want to explain this with a fairly non-technical diagram. When we talk about edge computing infrastructure placed at the edge of a mobile network, we refer to it as multi-access edge compute. Here, this is shown in the mobile edge cloud MEC column, which is the second column. You can see that an app media service hosted on the edge is being accessed by the end device through the red color data path. So this represents a data path which makes use of applications that are residing at the edge of the network. This is different from the traditional approach. Traditionally, the device or the user consumes applications that are hosted in a data center that is either global or regional, or that is part of the central data centers in the mobile communication network infrastructure, which host cloud service platforms. So this is represented through the green color pathway, where you see that it is much more longer because the application is actually not hosted at the edge, but it is hosted at a central data center that is very remote. When we talk about 5G use cases that require low latency, ultra reliable communication, the concept of edge computing infrastructure has a huge relevance. The reason is simply because of physics. A signal or data packet that needs to travel between a mobile device and the cloud, if it has to travel several hundred kilometers in order to be processed, this can lead to significantly large round trip times. These could be in the order of hundreds of milliseconds. So, when we talk about moving the edge infrastructure closer towards the network edge, what happens is we essentially reduce the distance that the packet has to travel to be processed by an application. So by bringing the application and the underlying infrastructure that hosts the application closer to the edge, we are able to reduce the latency and therefore able to support some of the more stringent constraints imposed by ultra reliable low latency applications. So in summary, the concept of edge computing or the edge cloud describes the use of the network edge to provide cloud services, as well as in many cases this would enable, for example, an application or the service running in the edge cloud to be migrated to a different edge cloud depending on the mobility of end user devices. So this is a key requirement for URLLC scenarios, because the multi-access edge compute becomes one of the most important elements of how next generation 5G services are built and handled. So for example, when an autonomous vehicle is in motion, the position of the vehicle keeps changing. So in many cases, the distance from the vehicle to the location of the edge cloud can change. So there is a need for a fast handover from one mobile edge cloud to another. And in a different scenario, for example, in a factory where things are not moving, the mobile edge cloud could be located on the customer side, in which case we refer to it as the customer edge. Now, when we talk about finally the overall concept of creating a fabric of multi-access edge computing infrastructure, we also think of a multi-tier model, which means that some edge compute infrastructure is closer to the user and other infrastructure that is deployed could be either at the central data centers or at the aggregation sites in between. So you have different levels of latency that can be offered, and obviously because you have limited capacity towards the edge, as you move towards the regional data centers and the central data centers and the public cloud, you have more and more capacity that opens up, but you have increased latency. The near-term opportunities for edge has also been significantly accelerated because of the impact of COVID-19. Across both consumer as well as industry, there is a need to fast-track economic recovery, which means from an industrial manufacturing standpoint or a transport and logistics standpoint, there's a lot of pressure that has been created in these segments, and there is need for automation-driven cost efficiency, quality improvement to accelerate the recovery of these industry verticals. In addition to that, new emerging areas like connected healthcare get a significant boost. Finally, the consumer demands for immersive experiences for entertainment and lifestyle services will continue to grow post-COVID. All of that sets really the scene to create new services through 5G and Edge. In summary, we believe that Edge is going to be a fundamental capability to drive the monetization of 5G. And across both consumer and enterprises, the power of edge computing would be seen in terms of the service innovation that gets enabled. When it comes to enterprises, also the requirement for a seamless edge experience would be a key requirement for market success. Now let's talk a little bit about what is Google's 5G and Edge vision and how are we working to make that vision happen. We have four key areas of priority. The first is to really bring cloud, and when we say cloud, we talk about compute, analytics, AI, ML capabilities to the edge of the network. The second is to really help provide a business platform to build 5G network and specifically edge applications. And then in many cases, amplify the edge footprint that a telco may have within a specific country with Google's global edge. And finally, be able to work with our telco partners and a developer ecosystem to really create new 5G and edge solutions with alternative revenue models. Let me now talk about how Google Cloud is building a portfolio of edge offerings. There are three key pieces to it. It includes a distributed infrastructure, an open platform, and a portfolio of 5G and edge solutions that is built as part of a partner ecosystem. When we talk about the distributed infrastructure, we are really talking about something that is both local as well as global. So as we explained earlier, the telco edge would be part of the telco 5G network across where the base stations are, across the aggregation and the far edge sites, and also at central data centers that are set up in a particular region. In addition to that, edge infrastructure deployed at a customer site is called the customer edge. This can be, for example, in an airport, this can be in a port, this can be, for example, in a factory floor. These are all examples of customer edge. Typically, the telco edge and the customer edge is part of a deployment that happens within a country. But Google also has thousands of edge caching and points of presence across the globe. This includes more than 2,000 Google global caches, as well as more than 150 edge points of presence across the globe. As we roll out our edge offerings, many of these edge points of presence potentially could also have Google Edge services being made available. Managing a distributed edge environment is not easy. This is because workloads can come in different shapes and forms, and they can be, for example, virtual machines or containers. They may have very different service management needs. There is not really one edge because by definition, edge is going to be distributed, and you need to have a platform that can operate across this distributed infrastructure. Additionally, it is important that edge fabrics are built on open modular platforms and not on closed integrated monolithic stacks. Finally, it is extremely important to have telemetry, observability, analytics, and automation across this entire infrastructure continuum so that with the right amount of insights, you can also drive, for example, automated placement of workloads, migration of workloads, and optimization of workloads to support the services that run on top of it. So, Google's Edge portfolio will be built on top of Anthos. Anthos is a unified open platform to build and operate multi-cloud 5G and edge applications. So the idea is to have a single consistent approach to developing, securing, deploying, and operating both network as well as edge applications. And the way we have looked at Anthos is that it should be an open application management platform that can be either deployed on Google Cloud or on other cloud or on-prem or on the telco edge or the customer edge. So in many ways, it is important to think of it as, for example, what Android was to the smartphone ecosystem. So the idea is exactly the same, to build an ecosystem of developers and applications that can run on Anthos consistently across any hybrid cloud, multi-cloud, or edge cloud infrastructures. To talk about Anthos in a little bit more detail, the idea that we have is that Anthos should support both IT as well as network and edge workloads. And in addition to being able to provide application runtime from a Kubernetes standpoint, Anthos also brings in several operational enablers so that security, policy, and service management can be done consistently across this underlying distributed infrastructure. This is a key tenet of Anthos. When we talk about building an edge offering on top of Anthos, the idea is to really try and bring a Google managed edge offering towards the network edge and the customer edge. And of course, part of rolling that edge offering is going to be working together with our telco partners who are building 5G and edge ecosystems. And our viewpoint is that we need to be able to create a cohesive, consistent cloud user experience even on the edge, and provide the ability to seamlessly deploy workloads anywhere, essentially where the workload should run best. This could be on the edge, this could be on the cloud, this could be on some infrastructure on-prem, and the ability to seamlessly move that workload based on operating needs. Finally, the idea is also that the edge platform that we build must bring differentiated capabilities optimized for AI, machine learning, for graphics and streaming workloads and other ambient computing use cases. So this would be on Google validated hardware, meeting different customer and application needs. So end of the day, what we really want to do is to bring and extend cloud services closer to the edge in a seamless manner to drive new experiences and outcomes for services that get built on top of it. Wherever there is a low latency requirement, then this sort of edge infrastructure could be hosted either on the customer edge. This could be a stadium, a retail store, an airport, or this could be hosted on the telco edge. In many cases, because of other reasons related to the volume of data being processed or the need for localized data processing, again, the edge location can be chosen. So latency is one factor, but there are other factors to be aware of. But the idea is that irrespective of where the workload runs, irrespective of whether it runs on the edge or in the public cloud, you have ubiquitous computing and optimal workload placement. And this is going to be a key factor for edge to work seamlessly. Finally, the end sort of goal for us is to sort of realize this effortless edge experience. So as a developer, you have the opportunity to deploy applications that you build on the edge, and this edge could be hosted within a telco network. You would have the ability in many cases to move a service seamlessly from one edge cloud to another, or to perhaps towards the public cloud in some cases. And in almost all scenarios, you do not need to know where the edge infrastructure lives. All you need to know is that you want your application to be deployed with a specific set of constraints, including location or latency constraints, and you let the platform take care of where it should be placed. Yep. Let's talk about now some of the edge portfolio solutions that we are building, and also talk about some of the specific use cases for edge. First, we are really focused on making sure that we can help telcos monetize their 5G investments. To do so, we are building a portfolio and marketplace of edge applications along with partners. So towards the end of last year, we announced a edge partner ecosystem where more than 30 different launch partners announced over 200 applications that can be deployed on the network edge. In addition to this, we are also working with telcos to build a number of end-to-end solutions. When it comes to customer edge deployments, what we call as private MEC, we're focusing on manufacturing, warehousing, mining, and connected venues, for example. When it comes to public MEC, we're talking about verticals like retail, transportation, airports, and smart cities. And finally, from a consumer standpoint, we are focused on cloud gaming as well as augmented reality as key areas where next generation services would get built out. When it comes to use cases for enterprises in Industry 4.0, there are a number of industry verticals where many use cases exist that can potentially be deployed through edge infrastructure and 5G connectivity. Today, we will focus on retail and smart manufacturing as two concrete industries where we will explore some different use cases. Overall, there's a lot of opportunity for innovation across other industry verticals like logistics and warehousing, mining, airports and ports, as well as utilities. Let's look at the retail use case first. When it comes to retail, a lot of retail stores have a lot of local infrastructure. And overall, there is a need to transform many of these traditional brick and mortar stores into smart stores. From a smart retail standpoint, we are now working with a lot of partners to really transform retail and bring next generation digital experiences to retail store shoppers. Some of the use cases in this space are really around transforming the way checkout happens. For example, these are contactless shopping scenarios where customers can check out seamlessly. There are other areas related to store management with regard to inventory management and with regard to also some in-store shopping experience management, which are top use cases for retail. Let me take a very specific example of something we have worked on in the past. We have had customers who really want to push new experiences when it comes to in-store shopping. So some of that could be in the form of, for example, facilitating shopper look, or in many cases could be optimizing the user experience in store with regard to, for example, queue management or inventory management and so on and so forth. So this is an example of a public multi-access edge computing deployment. So what you see here is a retail store that is connected through a 5G network to a public MEC infrastructure site. So a lot of the data generated in the retailer store is actually processed on this edge stack. So for example, security feeds or other video streams from the video cameras are transmitted over the 5G network and are routed locally to this edge stack in what's called local breakout. And all of the video analytics and AI/ML processing happens here, and then specific actions are triggered back to devices in the retail store. So the difference between doing this with a public MEC deployment and a traditional model is, in the traditional model, these data feeds would have gone all the way to the public cloud, in which case the latency would have been a lot more, as well as the cost of carrying the data all the way to the public cloud may have made this use case prohibitive from a commercial standpoint. Let's take another example, which is slightly different. This is the private multi-access edge compute deployment, or a deployment of a customer edge scenario. So this could be, for example, in the case of factory floors or logistics, warehousing. And here what you see is that the devices on the site are connected through a last mile 5G or 4G connectivity option to edge infrastructure, which is also located in the same customer site. So in the previous example, this was located on the network edge. In this case, we bring the edge infrastructure closer and actually deploy it on-prem. So this becomes a private mobile edge and multi-access edge computing scenario. So this is typically used when you need private connectivity, when you need ultra low latency. For example, you may have automated guided vehicles running on the site, for example, or you may have inventory robots that require low latency communication for coordination. So in many of these cases, you may not be able to have that latency requirement addressed through a public MEC deployment. So you will do it as part of a private MEC deployment. Let us now talk about specifically another industry vertical which is related to manufacturing. From a manufacturing standpoint, there are many opportunities for 5G and edge innovation. This is an excellent view of some of the key areas or domains within manufacturing where edge and 5G can be brought together to solve specific problems. These may deal with forecasting accuracy or better inventory management or improving machine uptime or managing quality assurance from a manufacturing standpoint in a better way. And a lot of this is based on improving the degree of automation within the factory floor environment. Let's take a closer look at this. When we talk about intelligent manufacturing, it is an important note that intelligent manufacturing can only happen when there is a core digital backbone that is bringing some of the key capabilities required to support intelligent processes within the manufacturing setup. This means that a number of different technologies need to be brought together. The connectivity part of this could come from 5G or other alternative communication technologies like Wi-Fi 6. But in addition to this, there's a lot of data being generated within manufacturing ecosystems, and there's a need to convert a lot of those data into insights that can drive optimal process management as well as operations. So some of the key technologies that we see should come together to drive new services for intelligent manufacturing would involve Internet of Things, as well as big data analytics, AI and machine learning, and cloud computing. This is, of course, in addition to the connectivity technology that is enabled through 5G. When we talk about implementing such a digital backbone for connected factories, we are really talking about unifying the data analytics and AI machine learning applied for manufacturing systems. We are talking about bringing intelligence into some of the automated quality and assembly activities. We are talking about how to automatically identify health and safety issues within the manufacturing factory floor. We are talking about process automation where, for example, digital documents are read automatically through AI services for document processing. And we are also talking about controlling the operational processes through adaptive control mechanisms and predictive control loops. So this is a complete view of how an end-to-end set of activities should be undertaken to really create smart factory operations. When we look at this in a little bit more detail and look at potentially the use cases that would come into play, these could be very different. So depending on whether you are looking at digital manufacturing capabilities and augmenting some of the processes in that space, this could be, for example, augmenting, personnel on the factory floor with AR, VR equipment, or it could be around predictive maintenance and quality assurance, or it could be in other related domains around logistics and warehousing, where you track personnel, you track equipment, where you use, drones and bots to drive, a lot of the automation, or you implement low-touch warehouses. All of these use cases will be built on some core and fundamental technology enablers. One of that would be connectivity. The others would be edge computation and devices that would rely on data and insights from applications running on the edge, and then different types of human machine interfaces. Some of the use cases specifically from a manufacturing and logistics related to manufacturing could be around predictive analytics for supply chain management, could be around AI/ML augmented processes, and we will see this in example. So this could include vision-based AI machine learning control. This could include, for example, some drone-based systems to drive predictive maintenance and operational inspections. And this could also be, for example, smart inventory management and logistics. So these are some of the key areas where it is possible to drive a lot of service innovation. The foundational technology to drive this service innovation, in our view, is actually a number of different core enablers which are brought together. The first is, how do you manage infrastructure that is existing in a factory floor or in a manufacturing setup? So how do you connect information technology systems like SAP that are typically used for supply chain with operational technology systems that drive PLC control, for example? The other aspect is, how do you really drive industrial IoT at scale? Because factories generate a lot of data because they have a lot of equipment. To be able to use that data to drive optimized processes is really a challenge. And this is something you want to do at scale and you want to do effectively. How do you apply AI and machine learning at the edge on the factory floor and really drive specific industrial AI solutions built to optimize these process flows? And how do you bring it all together with 5G connectivity, for example, deployed along with edge infrastructure? Let's start with the first block, which is combining IT and operational technology together. You would recall that when I talked about Anthos as an enabling platform, I spoke of how it could be used to manage both distributed edge infrastructure as well as infrastructure on-prem. This is exactly the idea here. Anthos can enable IT and OT application management to be done across both hybrid and multi-cloud environments. So if you're running a factory that exists in 4 countries and you want a common infrastructure and application management platform across these 4 countries, so that you can have workloads on-prem, you can have workload on public cloud number 1, public cloud number 2, you would go with something like Anthos that enables you to set up hybrid and multi-cloud operations and integrate both IT and operational technology applications. In addition to managing the IT and the operational technology platforms in a smart factory environment, it's also important to be able to manage the devices that exist on a factory floor and process the data that comes from these devices. Specifically, industrial IoT connectivity requires both management of large device farms and then processing of data from these devices in real time with maximum security and operational scalability. In order to do this, there are a number of cloud services available, and Google Cloud offers the Google Cloud IoT Core, which is an open hardware agnostic platforms that can securely connect to a large IoT device ecosystem and then process the data from that device ecosystem and then connect that data to analytics and AI/ML services so that a lot of closed loop actions can be managed. This can be used to drive optimization and efficiency in different workflows. This can be used for real-time control of some of the production process analytics workflows. This can be used for scenarios related to predictive maintenance. Typically, the idea is to make sure that you connect devices, gather information, and then from that information, create insights that can actuate action. So this is an end-to-end process where devices get connected to an edge gateway and from then use either a 5G connectivity or an alternative wide area network connectivity to connect to the cloud service. The cloud service ingests the data and then triggers business process workflows and data processing pipelines to process that data, and in many cases uses analytic services and AIML services to generate insights. These insights can then be used to drive closed loop process control. Let's take an example of how we can bring this all together. This shows a device that is generating a lot of data that gets pushed into the cloud IoT core. When that data gets pushed into the cloud IoT core, the cloud service then triggers either events to be processed, or it can trigger a data processing pipeline that can push this data into an analytic system. The data in the analytic system can be used to really drive training of different AI/ML models, and these AI/ML models can then be pushed back into the edge device so that the models are optimized on an ongoing manner. An example of this for predictive maintenance of equipment would be to, for example, collect information from vehicles that are used in a manufacturing setup through a gateway device, and then, as explained earlier, process it through an IoT service that can use that data to drive event-based responses, or create a data pipeline to persist that data and store that in a data lake for long-term analytics needs. These analytics needs could be, for example, scenarios like predicting the need for parts, or this could be for anticipating the need for technicians to handle vehicle breakdowns, or this could be, for example, to drive other actionable business outcomes. We will see later how such an actual end-to-end service is built on GCP. Another example of intelligent process control is a scenario where equipment on the factory floor are controlled through some sort of edge controller, and the edge controller actually runs AI machine learning models. These models are trained on the public cloud, but once the model has been built and trained and verified, it is then deployed on the edge controller, and the model then controls industrial processes locally without any need to connect to the public cloud. So this is an approach that can drive, for example, localized intelligent process control on an ongoing basis. Let's look at how, for example, some of these AI machine learning scenarios can be supported on the edge. Typically, when it comes to the application of machine learning and AI on the factory floor, some of the key considerations are related to the cost of doing this, whether it can be done in an online fashion, because many of these manufacturing facilities may be in remote locations with poor internet connectivity, whether latency requirements for critical process control can be met, and in some cases related to the privacy of the data being processed. In many cases, it is possible to use edge solutions that combine hardware optimized for industrial AI processing with software solutions built on top of these AI frameworks that are supported. Coral is an example of a hardware and software platform from Google that allows AI application to be built and deployed on small edge devices. And within these edge devices, there is an edge TPU, which is a high-performant chipset built for AI applications. So the idea is that you can run powerful AI machine learning algorithms on the edge after training them on cloud. And when you run them on the edge, they are deployed in an environment where connectivity is limited and everything is done locally. These are used typically for use cases related to quality control and visual inspection of manufacturing processes. This can also be used for predictive maintenance or worker safety monitoring. The edge TPU in this particular case is a chip that is very, very small, that's optimized for vision applications, as well as for TensorFlow light-based AI model processing on the edge. This can be incorporated into devices using different form factors. So if you're a developer, you typically get started with a dev board, but then there is a system one module, as well as there are additional TPU modules that are available to be integrated into a number of edge devices that could be manufactured by third parties. So these come at different price points. As you can see, the edge TPU module retails at about $20. And in addition to that, if you're looking at a developer board, then you have a number of options available for this. These custom edge solutions, then on top of the hardware that was shown earlier, can be combined with, for example, services on cloud that can be used to deploy AI models on hundreds or thousands of devices on the factory floor. So if you have a manufacturing setup where there are many remote edge devices, in order to be able to manage the life cycle of AI models that are running on these edge devices, you need some sort of centralized capabilities, which is also available on Google Cloud. The service, we call it as Google Cloud Edge Manager for machine learning. So this enables the AI models that are deployed on these devices to be updated on an ongoing basis. And it is not just for Coral hardware. The Edge Manager for machine learning service can be used with any hardware that is compliant to a few standard interworking requirements. So when it comes to the use of AI in production, the view that we have taken is that industrial AI requires a number of critical capabilities around data acquisition, data processing, and the use of AI machine learning algorithms that can be built very easily. So typically, there is a need to ensure that we have the ability to build quickly AI models. And one way to do that is to actually use AI to automate the process of model generation, which is what we do with Automl. So when we talk about Automl, or the use of AI to generate other AI models, one good use case category is around visual inspections. So this is usually required for predictive maintenance or quality assurance across a number of different industries. And it may drive, for example, anomaly detection, safety, predictive maintenance, and quality control processes. For example, in electronics, it is extremely hard to find certain cosmetic defects manually, but it's quite easy to do that with visual identification enabled through AI. Similarly, in the automotive sector and the semiconductor sector, there are a lot of different scenarios where automating the quality assurance process will eliminate the need for manual and time-consuming quality assurance checks. Visual AI holds great promise to solve several real-world problems, from aerial inspections to detecting glaucoma in retinal images to performing geological analysis. Let's take the example of aerial inspections done at scale. AES is a Fortune 500 global power company owning and managing more than $33 billion of assets. They have developed multiple innovative drone and robotic solutions which are used to drive safety hazard identification and inspection of company assets. Their drone inspections produce thousands of images for each wind farm. So if these images were to be analyzed manually, it would take weeks to identify cracks, rust, or other defects that require repair. By working with Google's AutoML Vision, they have deployed a high-quality custom model that automatically identifies defects and labels them and reduces the number of images requiring manual human review. So let's see how they have achieved some of the results using AutoML Vision.
Global warming is one of the big challenges of our times, if not the biggest challenge of our times. Now, we really do have the technology to address the issue of carbon footprint greenhouse gases from the electric sector. The ACE Corporation is one of the leaders in new technologies for renewables and energy storage. It's a Fortune 500 company. Our mission is accelerating a safer and greener energy future.
Right now we have around 8 wind farms. Each farm has different capacity, starting from 50 turbines up to 300 turbines.
They cover large spans of geography and land. They're spread across hilltops and mountainsides.
All these turbines need annual inspections. Originally, it could take up to 2 weeks to do one inspection. We partnered with leading drone service company Measure. Right now with drones, we can do it in 2 days. And this is safe and quick.
For a wind turbine inspection, we go out with our pilots, and what we're looking for is cracks or defects, things that may need to be repaired.
On a typical inspection, we're coming back with 30,000 images. Spending 4 weeks reviewing images, I don't think anyone's going to argue that that's the best use of a highly trained engineer's time.
How do we speed that up and how do we make it 10x more efficient? That's where machine learning and AI comes in.
We've built a great end-to-end solution using Google Cloud's tools and platform. With the Automl Vision tool, we've trained it to detect damage. We're able to eliminate approximately half of the images from needing human review. The remaining 50% of their time can now be very focused on identifying that damage and really determining the right course of action to remediate it. Moving from reviewing images to training machine learning models, it's a much higher order employment opportunity for people and one where we're trying to develop our team. Google Cloud has been a great partner. Their technology is consistently among the world leaders and they're just a great partner to work with person to person. At the end of the day, we won't reach the cleaner energy future without advanced tools like machine learning.
Technology will allow renewable energy to be cheaper than conventional energy. Artificial intelligence, robotics, this is really what the future is all about.
Automl is technology that automatically creates machine learning models. It enables developers with limited machine learning expertise to train high-quality models specific to business needs. So the idea is you build your own custom machine learning models in minutes. And the way Automl does that is that it automates the entire process from data pre-processing, model design, to deployment and retraining using a simple UI-based approach. So the way it works is that customers simply upload the training data set and the Automl framework does the rest. So this is using the latest AI research and technology from Google, and it builds hundreds of models behind the scenes and picks the most accurate model. And this all is enabled through a simple to use REST interface. This is one of the reasons Google Cloud is ranked as a leader for Vision AI products. What's so special about our approach to visual inspection is that it's particularly easy to deploy, which means it's quick to set up, and thanks to the way the pre-trained models work, the number of images required to actually train a new model is massively reduced. It's fully integrated with the other Google Cloud AI stack offerings, which makes it easy to deploy this across a number of adjacent use cases. We have a number of customers who use this to drive visual inspection for production processes using cameras to scan and analyze the quality of products coming out of the production lines, and who also use it to drive worker safety and health using AI to monitor compliance to safety regulations, for example, in a manufacturing floor. Let's look at one final example of machine learning at the edge. This shows a quality assurance scenario in a manufacturing process for cars. So here at the quality control station, you could have a number of cameras that are inspecting the manufactured car to look for defects. In many cases, these defects can be identified on the spot and then alarms raised to rectify the quality of the end outcome. In many cases, this information can also be used to retrain the model to improve the efficiency of the model, and typically such a retraining process would involve uploading these images back into the AutoML service in Google Cloud and using a human to review some of these images, relabel them if necessary, so the quality of the guideline improves. And then once the model is retrained, to take that retrained model and redeploy it back on the edge device so that the improvements in the model can take effect immediately. So this is typically how machine learning at the edge would work. Finally, all of these technologies combined together with the 5G network connectivity that is made possible through telcos would really create solutions that can scale within the context of connected factories. Hopefully, this gives you a good idea of some of the practical use cases that would come into play in real world scenarios. And as you think about your own idea, gives you an opportunity to also think about some of the different Google Cloud services that you can use to bring these ideas to life. Thank you for being with us in this session and looking forward to have you in the subsequent sessions.
Welcome to this next session. Today, or in this session, we're going to be covering AutoML. So first, we're going to cover some slides and some content to give you an understanding of what AutoML is. But a picture is worth 1,000 words, so we're going to spend a lot of time looking at demos as well, which are pretty exciting. So let's get underway. So first, let's just talk about machine learning and artificial intelligence. So artificial intelligence here, as you can see, is a discipline, and machine learning is a way of solving specific problems in artificial intelligence. But the learning curve, or the cost of entry with machine learning, is very high. In fact, if you recall with Google, we first started with TensorFlow, and then we provided tools on top of that, or after that, that allowed you to easily run your machine learning models on Google Cloud. And then we launched additional machine learning products to make it easier again. So if you think about it, we kind of got it the wrong way around. We actually started with the hardest thing first and then said, now that you've learned the hardest possible thing there is to learn, which is TensorFlow, we're going to give you a set of easier tools, and then we're going to give you another set of easier tools. And then what we should have done is actually reverse that. We should have said, we're going to give you an easy way to get into machine learning. And then if you like that, you can go to the next step and do something more complex. And if you like that, you can go to the next step and go to even more complex with using something like TensorFlow. So AutoML is an attempt to turn that learning curve pyramid upside down and to give you the easiest entry to machine learning possible, so you can get the benefits of machine learning without having to do all of the hard work. And then once you understand the benefits and you want to commit to a machine learning journey, then you can keep going and start to train your own models and host those on Google Cloud. And then, of course, use something like TensorFlow to create your own models. So if we look at that machine learning journey, this is the first thing we need to do, right? We need to train an ML model. And to do that, we need to come up, firstly, with a lot of data, which can be a challenge in of itself. And then we need to have that ML model we can train using the data. Now, this is why data scientists make a lot of money. The ML model is a mathematical function, and often, data scientists build this model up from scratch, or they'll take an existing model and modify it. And this is not an easy job. Okay, there are many, many research papers and all sorts of things, and GitHub is full of machine learning models to show you how difficult this can be. And this is what the TensorFlow library is for. The second part is to predict with a trained model. So in this case, we're taking an unlabeled photo, passing it into our machine learning model, and then getting an answer out the other end, which in this case happens to be cat. So which is the part most important to most people? It's not training the ML model. That is not the part that's most important. That is just a means to an end to achieve what they really want, which is to actually be able to get predictions from that model. So how can we shortcut that model creation process and get as quickly as we can to the actual predictions themselves? Now, on Google Cloud, we actually already have a whole lot of pre-trained machine learning models that you can use straight out of the box. So that's things like Vision API, Speech API, Video Intelligence, for processing videos, natural language translation, and so on. However, there's one small problem with these models, and that is they're a black box. What if you have data that you want to make predictions on that doesn't quite fit the pre-trained models that I'll give you? For example, you want the Vision API to recognize specific places or specific people, or you want the natural language API to understand very domain-specific language. For that, you can't use our existing APIs because you can't change them or modify them so they can understand additional or new things. Again, this is why we have AutoML. So AutoML is our machine learning offering that creates a machine learning model for the problem that you give us. The key here is that You don't need to worry about all the stuff that goes on with models. You don't need to know about training the model. You don't need to know about tuning the model. You don't need to know about hosting the model. You don't need to worry about any of that. All you need to do is give us a data set, tell us what's in that data set, and then we will generate the predictions for you. You don't have to do anything else. So as a result, you can get up to speed and start actually getting the benefits of AutoML almost immediately. And because it's deployed on Google Cloud Platform, you get all the scale and all of the really good stuff that comes with that. And of course, like Google is a machine learning company. Nobody can argue that Google is not a leader in machine learning. And so you get the benefit of that. We can also do human data labeling if you need to, as you can see here at the bottom of the slide. But in most cases, customers will come to us with data that they already have labeled, or they can outsource that data labeling themselves. So we have lots of different AutoML flavors. And here is the main ones. So we have AutoML Vision, so you can teach a model what to look for in a picture. You can also do AutoML Video. AutoML Tables is a really fast and easy way to run AutoML prediction on a large data set. We also have natural language for things like analyzing what's in the language, extracting entities, extracting sentiment, and so on. And we also have AutoML Translate. Now, I think Translate is particularly interesting because one of the benefits of AutoML Translate is you can augment your translation with our already huge translation approach. So what happens is you tell us what additional work we should do when we translate the content for you. So what happens is that we translate the system using Google's translation machine learning, and then we basically do a second pass based on your model and combine the results. And so you get like a best translation for your specific situation. Now, it's really important to note that all of the data that you put into ML, or AutoML, sorry, is your data. We don't let anybody else use your data. We don't take the information from AutoML that you've put in and use it to build up our other products. None of that happens. Your data is always your data, and we will never, ever touch it without your permission. So that is really, really key, in that you can be pretty safe putting things like your IP and other interesting data in there and do some really interesting groundbreaking stuff, knowing that it's always going to be yours. And of course, you can always take it back out again if you need to. So how does it work? Well, based on the data that you provide to us, we run the data through essentially a machine learning engine that determines what is the best machine learning model to apply to your data. So we actually use machine learning to apply yet more machine learning. And then once we have evaluated all of your data against all the different models to see how well they work, we will then select that individual model and do a proper full training against it, again using your data. So you don't have to worry as to whether something like regression or nearest neighbor or mean squares or matrix factorization, you don't have to worry about those words. You don't have to worry about those models. We will determine what is the most appropriate model based on the use case that you're defining to us. And then we will then use that model, and so you can make predictions. So, and it's derived, not surprisingly, from our best-in-class research. So all of our research that we've done across machine learning, and here's some of the research papers that we've done, talk about apply this to your individual problems. Okay, so that's just a little bit about ML, AutoML. I am going to talk a little bit more about ML at the end of the demos, but for now, we're going to dive in and look at a whole bunch of AutoML demos that have been put together, and we'll run through them each, and I'll talk about them, and then you'll see them actually working and predicting. And then, of course, we'll have a bit of a think about how you might have a bit of a think about how it might apply to your individual individual situation, or how you can adapt the AutoML products to your own specific situations. And I'll try and think up some as we go along as well. So the first one we're going to be covering is natural language. And to look at natural language, we're actually going to be downloading, or we have downloaded, the movies dataset from Kaggle, and here's the dataset screen. And so what we're doing is we're downloading the metadata from over 45,000 movies. We've brought it into AutoML, and what we are going to ask the ML model to do is, based on the language used within a piece of text, can you please predict the genre of the movie that is being talked about in the text that I pasted in? So what we've said is, use that, dear AutoML, please take all of the data that you know about the text, apply some natural language to it, and then based on basically the internal score that you get out of that natural language, associate it with the genre of the movie. So here is what it looks like actually in our natural language interface. So we can see here that we've imported a huge amount of data. Now, you don't need to import this amount of data. You can actually get going with as little as 100 samples per category. So if I was going to do this myself, we can see down the left-hand side here, we can see all of the different genres. And I could import 100 précis for action, 100 précis for adventure, 100 précis for animation, and so on. And that is all I need to actually start with machine learning. You don't need terabytes and terabytes and terabytes of data. So here we are. Let's have another look at that. So here we can see we've got 42,000 labeled items, and each of these has the précis, and then each of these also has a label, which is the genre. And then what we did is we trained our model, and I'm not going to go through here, but we trained our model to see run, and we can get an idea of the model evaluation, and we can go in and we can actually see how well that model did training on the data that we gave it. And so we can see we have 4,000 test items with a precision of 70%, and you can see the recall and the precision charts here, and you can see all the various predictions here. And it's actually not looking too bad for a first run. So remember, AutoML is not designed to be perfect. Okay, if you want perfect, that's where you start creating your own machine learning models. What AutoML does is give you as much benefit as possible in the shortest time possible. And so you're going to see some places where it doesn't quite work. But with a bit of tuning and a bit of tweaking, you can, of course, get additional benefits out of it. And we can see here one of the things that we can change is the confidence threshold. And we can actually use that to adjust how much data comes back. So actually, our model's looking pretty good. So now we can test it. But of course, we need some data to test our model on. So I thought it's not very interesting to just input a fixed piece of text, because that doesn't actually tell you if anything interesting is working, all right? Because it might be text that I've prepared to get the best result out. So what I did is I found a website that generates a random plot. So what we can do is we can just change a few words. So we'll change a few words so you can see that they are done, and it's going to write me a science fiction plot. So in this case, it's a science fiction movie. So here it is. So it's called Galactic Ribbed Blade Wars. So I am going to take a bunch of text here. I'll just grab that. And I'm going to go over and place it in our evaluation model. And then we'll just ask the model to predict. There we are. And if we look down the side here, we can see that it has, with 96% confidence, predicted that this is a science fiction movie summary, which is exactly right, because the site I was using was a science fiction movie plot generator. And we can see how confident it is with other genres. So it's only 66% confident that it's action, 64% horror, and that's because there's words like ghost and zombie in there, and then it drops off very, very quickly down to 27% for fantasy and so on. And right at the bottom of the list heading will be documentary. Who knows? It could be true. So this is great. We're just looking at it in a web browser, but that's not very good. How do you use it in real life? Well, if we scroll down, we actually, as part of AutoML, give you examples of how to use your custom model in the real world. So here we provide the JSON you need if you want to call our REST API, and how to call the different types, and how to finally make a request. You can just set hiding at the bottom here. But more importantly, we give you a programmatic view of how to actually call this and predict against this AutoML model in Python. So you can actually take this piece of Python here, modify it to include your file paths. You can see here, run it, and you're good to go. Okay, so literally in minutes, you're now getting a machine learning prediction result from this AutoML model. And of course, as I said earlier, because it is Google scale, you can use this in production with no issues whatsoever. Okay, so that is a natural language. The next one we're going to move on to is vision. So in the vision API, you can take an image, or images, I should say, and again, remember, you only need as few as 100, and tell us what to look for in the image, and we will then use that as further as a machine learning model to then determine, make predictions about the next types of images. And we're going to look at two different types. The first one is like a classification of an image, and in this case, we're going to use chest X-rays. And then the next one we're going to look at is object detection. Now, there's lots of different ways that you can use classifications of Vision API. For example, a couple of really interesting things I've seen is a demo using Game of Thrones TV series where we actually labeled the actors, or we labeled the character names, not the actors. So then, because we were able to extract individual frames and we knew where the frame was, we could then ask AutoML to do a search for us for a character name. So I could say, show me anything, any spot in the first season where the character Daenerys Targaryen appeared. And then, because we knew the frame number and every frame was timestamped, we could then actually extract that timestamp and actually go to the video and play the video from the exact moment that Daenerys Targaryen showed up in that episode. The other interesting demo I've seen was actually from the TV show Westworld, where they indexed images using ML Vision based on the location or the set location in the TV show. So rather than a physical location in the real world, we did a machine learning AutoML Vision data set of the names of the location of the TV show. So the such and such saloon, or the medical lab, or the offices, or the control room. Forgive me, I can't recall the exact names of everything from the TV show. And then again, you could do a search to say, show me everything, any images of this particular location in that particular episode. Now, you can also combine this data with other data about this imagery. So, for example, if you take the same imagery that you're putting into AutoML and pass it through our Vision API, we can identify all the other metadata that you might want to know about, but you can have us look after. So that includes things like color palettes, locations, objects, all sorts of things. So then you can start to really build up a really, really rich corpus of information. So again, just using a Game of Thrones as another example, we could train our AutoML model looking for specific characters, but then have the Vision API look for objects that it knows about, or labels that it knows about in the image. So, for example, a horse is probably the really easiest example. And then, therefore, we can say, okay, now show me pictures of Daenerys Targaryen where she is in the same shot as a horse, or show me Daenerys Targaryen where she is in the same shot as a dragon, because our Vision API knows about things like dragons and horses, but it doesn't know about the character Daenerys Targaryen. Or you could even say, show me images of Daenerys Targaryen where the overall tone of the image is yellow. Or show me pictures of Daenerys Targaryen where she's smiling, because facial expression is something we can extract from our Vision API. So by combining these things, you actually can get very, very rich metadata, very, very rich search facet combinations that you could not get before. Okay, that's enough talking. Let's have a look at some X-rays. So what we have here is a data set of X-rays showing different types of pneumonia compared to normal chest X-rays. And so what we did is we took these chest X-rays and we loaded them in to, again, our Vision AutoML model, and we labeled them to say, are they associated with pneumonia or are they associated with normal X-rays? Now, to my eye, yeah, they look more or less completely the same, but the system is able to determine that they are indeed different. So let's do a test. We've got our model here, and I'm going to upload an image. Let me just find the folder here. Here we are. Okay, so I've got some normal and pneumonia images. So I'm going to grab a sample. I've just picked a random one here. I'm going to upload that, and our system is going to now run this prediction against the model and determine what the outcome is. And we can see here that the system has determined that this is a normal chest X-ray with an accuracy of 92%. So let's run that again, and this time we'll use an image associated with pneumonia. We'll load this one up, and you can see how, by the way, how quickly it returned. And this one now has a probability of 96% of pneumonia. So really simple to run and really simple to train. You can just see we just gave the system a bunch of images. By the way, this is typically done in a CSV format, and we got an answer straight away pretty quickly. And again, if we scroll down or we look at the deployment, we can actually we'll get the JavaScript and the Python that we need to actually execute that model as well. So very easy to make these types of requests. All right, so that's one aspect of images. The other aspect of images I talked about is object detection. So here we have an airport. And what we are training the AutoML vision to do in this case is to look for planes. So this is all satellite imagery of aircraft. And what we've done in the model is we have identified every plane that is in this image. And you can actually see here, this is the model training. And you can see here that every model is outlined. And this can be done manually. Normally it's done manually. And so, model labeling is a big issue and a constant challenge for people. And we can see all of the data associated with our planes. And we uploaded here, we uploaded 820 images of planes. And we said this image has planes and this image doesn't. And then again, we told the model, AutoML, to go off and train based on what we just told it and prepare that model for us. So you can see the training here. So everything's looking pretty good. Precision and recall, you can see very good, I think. And we can evaluate it and we can get all the evaluation data. Now, AutoML evaluates this for us. We just have to create an evaluation, carve out an evaluation set when we do the labeling. And it's done a pretty good job of labeling our data set. And as I said, if we need to, we can dial the thresholds up and down to tell us how well or otherwise it's performing. And then finally, of course, we can actually test to see it's working. So how do we test to see if it's working? Well, what I did in this case is I went online, just did a Google image search and said, looked for a satellite photo of aircraft. That was all I did, and downloaded an image, and we can make use of that. So here's our image, and we can see that it has some planes in it. And again, we're now running an Automl prediction, and it's popped up the results pretty quickly for us. And you can actually see it's highlighted in green here where it's identified a plane. And if we mouse over each plane, we can see that it's done a pretty good job of identifying them. However, you can actually see there's a few places here on the edge of the image where it hasn't been able to identify those planes. And in this particular case, I would say it's due to JPEG artifacts, and this is actually a low quality image. So the model had a bit of trouble identifying them based on those JPEG artifacts, which also tells us that part of the challenge of coming up with good images to train the model on is, of course, its quality itself. And again, we have callouts here, so you can use Python clients or our REST API in order to use the model as well. So again, we guide you through the whole thing. So very, very cool. All right, so that is 2 ways that we have used our Vision API. The next one we're going to talk about is our document layout AutoML model. So what we're looking at here is we've taken a data set where we wanted to identify all of the tables and diagrams and figures in a set of research papers you can see here. So we obtained a set of all of these and we labeled them. And if we click on one of them, you can see the labels here. We've outlined this and labeled it as a table. If you go to this one, you can see we've outlined it and we've labeled it as a figure. And again, we've taken, given this to the AutoML model and said, okay, isolate these items from the image. So again, we'll test and we'll test this. And actually, the funny thing here is that we're using a paper called Machine Learning Based Anomaly Detection of 5G Networks, which weirdly I had hanging around on my hard drive, and I think it's very current for this demo. So here we are. We're just going to grab the screenshot from that particular research journal paper, and it's going to analyze it for us. And it's popped up all of the different figures that we have. So it's found this figure, this list at the bottom, because it's got bullets, and this figure here also on the page. And it's found that all of them with 99.7 and 99.8% confidence. Now, one of the things you might notice here is just like the planes, as we mouse around, the bounding box actually jumps to those things, and we make the bounding box available in the result. So this means from a machine learning thing, you can actually then, based on that bounding box, automatically extract or cut the contents of that bounding box from the prediction itself. So if you have a lot of documents that you need to get through and you want to extract the imagery, you can just upload, thousands of these documents to Google Cloud Storage, run the AutoML model against them or the prediction against them, capture the bounding box, snip the image out, and you've got the figure automatically saved. And there's lots of different ways that you can string a solution like that together on the Google Cloud Platform. One thing we're not talking about today, by the way, is a new product called Doc.ai or Document AI, which also is a document parser. So, and it's kind of like AutoML, but we take care of the heavy lifting for you in terms of identifying the document and extracting text from it. So if you have a lot of invoices or you have a lot of bills or handwritten application forms or anything like that, you don't even need to train Google to look out for them. You just hand us an invoice and we will say, okay, we know that this is an invoice based on what we know about every other invoice we've seen, and we'll extract all of the different fields from that invoice, including, the payment dates and who sent it, and the line items and the total and the payment terms and all of that sort of stuff. We'll extract using ML and make that available to you. And that's a super, super cool product as well. But we're not showing it to you today. But yeah, I really love Document AI. Okay, so that is again a little bit of Vision API. Okay, everyone, it's time to take a break. So get up and stretch your legs and walk around, and we'll see you again in 5 minutes. Thanks.
Really flying the music. Okay. And it's so packed in here. The band sounds great.
All right. The next one we're going to take a look at is AutoML tables. So AutoML tables is a really great way of getting machine learning insights from tabular data. And when I mean tabular data, what I'm really talking about is a database. And so, dealing with lots and lots of data and trying to figure out what is the right way to approach it for getting predictions or doing additional machine learning-based analysis is really tough. So one of the ways we approach this is to come up with AutoML tables where you just basically tell us the parameters of the table or the data, tell us what to predict, and we'll take care of the rest. So this demo is actually going to be using the Titanic machine learning demo, or the Titanic machine learning data set. So what it actually does is it looks at the profiles of the passengers of the Titanic and actually predicts whether that passenger perished in the Titanic sinking or not. It's a little ghoulish, I admit, but it's a pretty special demo. Okay, so let's take a quick look at the data. So here you can see what we've done is we've said, here is all the data that we want to track. So the age of the cabin, the fare, and so on and so forth. And then the target is, did they survive, right? So what we've actually said is take all of these values and then to use it to build up this concept of survivability based on what you know. And again, we can go through and we've got the models here. We can evaluate it, so we can take a look at the full evaluation and we can see how well it's been running. And the feature columns, so we've included 10 feature columns. So these feature columns are the things that we will actually use to predict the survivability. Okay, so you can see here the class of the, what passenger class they are in, sorry, their sex, their age, all sorts of things, how much they paid, and of course, did they even get on the boat? Now, if they didn't get on the boat, clearly they survived. So, but let's take a look at this. So here we have some data, and we're going to do what we call online prediction. So we can do batch prediction, and that is we can take an existing data set from BigQuery or a CSV file and actually push all of the data through and then export the data back out again. So if I have 1,000 rows of data, I can just, or 10,000 rows, I can just pump it in and get the data back out again, back into BigQuery or back into a CSV file. But what we're actually going to do here is just do online prediction, which means we're just going to do it right here in the browser for an individual record. So what we're looking at here is each signal column. So we can see the fare, the name, the class, the gender, the age, and so on and so forth, and where were they. So we can then run a test against this and predict how it went. So let's actually run that prediction. And based on all of those facets, we can predict that the person likely survived. Possibly because they were female and women, and children went into the boats first. But let's change that and let's make sure that they didn't spend as much on the fare and a male was less likely to get into the boat. So let's predict on that. And you can actually see now this person had a very high likelihood of perishing in the disaster. Now, the reason I lowered the fare is because that means they would have been staying in one of the lower class cabins, which were below decks, and it was very difficult for them to get out during the sinking. So they were less likely to have made it to the deck. And if they did make it to a deck because they were male, they were less likely to get a spot on a life raft. So, but I'm making that prediction based on what I know of the Titanic sinking. Now, AutoML knows nothing about the Titanic sinking. It only knows the data. So here what we're doing is we're actually playing with the data itself. But you can think of this in lots of different use cases. So, for example, what is a person's propensity to buy? What is the customer's propensity to churn? Has the customer purchased a high-end handset in the last 5 contract renewals? So what is their propensity to, what is their percentage chance based on demographics, based on age, based on location, based on everything you know about a customer and their past purchasing history? You can then generate a confidence of them renewing their contract again with a premium handset. Now, you don't have to do anything here. You just literally need to tick a few columns and the system will actually start to understand it yourself. Now, again, as I said, it's not perfect, but if we can predict, better than chance, or if we can accurately predict, say that, 80% of your customers are going to behave in the way that the model predicted, that is a significant increase over basically chance, right? And then if you want to get to 85% and 90 and 95%, you may go down a different road, for instance, using something like BigQuery ML. So BigQuery ML is kind of like AutoML tables, except you generate your machine learning models inside BigQuery, directly use inside your SQL statements, and will actually generate the model right inside the SQL, and you can query that right inside the SQL. And so when you create the model, you can actually tune the parameters and get a finer grained set of predictions based off the data, and you can actually specify the model type that we're going to use. So that will maybe get you to 90% accuracy just using some random numbers here. So if you want to go to 95, you then might start to apply custom models to the data that you have. And then on and on you go. And so you can think of lots of ways that you could apply machine learning predictions, mean time to fault for network equipment. Who knows? Lots. I can't think of another example at the moment, but those are 2 good ones, right? We've also done some really interesting stuff around contention and congestion in mobile towers as well, using machine learning. So we've looked at in the past for some customers, based on the time of day and the machine learning, based on the time of day and the cell tower, how likely is service to be degraded at that particular cell tower because of the congestion of people around it and things like that. So there's lots of different ways that you can spin views of this tabular data. So yeah, lots of fun. All right, let's move on. Keep going on to the next one. Told you there was a lot of demos. So the next one we're dealing with is translation. So remember I talked about with translation that we can take our existing Google Translation API and you can train an AutoML model that sits on top of that and augment our results with your specific use cases. So the data set we're using in this specific demo is the very excitingly named European Parliament Proceedings Parallel Corpus, and we're actually going to be training it on 15 years of data from the European Parliament. And so what we did is we imported the Spanish to English translations of this data set. And we said, okay, translation, now that you know the parliamentary style of languages that is being used and the political type of language that's being used, we want you to better understand how to translate from Spanish into English, accounting for all those specific words and the specific ways of speaking within that type of situation. And so what we did what I did here is, just to show you, I took a random file off the internet. The challenge for me was like, how can I show you a random Spanish phrase being translated by AutoML? So this particular PDF has nothing to do with the European Parliament. It is a piece of text that is a statement by the Spanish Prime Minister. So what I'm going to do is I'm going to copy a paragraph of text, And I'm going to use that in my AutoML demo to show you that even though we're now using a piece of text that the system has never seen before, it's going to be able to translate it into Spanish. Okay, so here is our training model. And before I do that, I'm going to just go over and show you all the sentence data that we have. So here is all the sentence data. You can see the source and the target data that we are going to use. And we trained it up, and you can actually see that there's almost just shy of 2 million sentences that we're going to be training. So it's a very, very large data set. But again, you don't need this scale. Of course, the more data that you have, the more accurate that it's going to be. Anyway, so let's run a prediction. So I'm going to paste some text in here. There is my text, and we're going to translate that. Let's give it a moment. Just talk amongst yourselves. There we are. So there is our translation. And it also offers us a comparison between our model and the our model and the default Google Translate model. And we can actually start, if we look, it might be a little hard to see. Let me make it a little bigger. We can actually start to see some differences. So, for example, here in the sentence here, it says the reversal of the outlook. Instead is here the inversion of perspective. And here, the most joyful consequence of Europe's new direction is better than the most joyous consequence of Europe's new course. So quite different words, or not necessarily, but the subtlety here is that individual words can have quite a big difference in the way that we translate individual documents, or alters the tone of the individual translation itself. So you do really want to make sure and get it right. So that's just a little example of doing a translation and then putting it in. And of course, this can work with lots of different languages. So if you have the data set, let's just say from Tagalog to English, or Tagalog to Cebuano, or what have you, if you have the data, you can load it in and augment our translation API. And I think that's a really interesting one. Now, one question you may ask is, can you do it for a language that we don't know? For example, can we translate Bicol into English? And the answer, unfortunately, is no, we don't, because it does rely on using one of the languages that we already have support for in our translation API. So, unfortunately, if you are from Bicol, we can't translate the Bicol language into English. Okay, so moving on to the next one. Now we're going to talk about some more about language processing, or natural language processing. And we're going to talk about sentiment. So this is whether a person's happy or sad or neutral. So this data set we're using, again, is quite a well-known data set, which is the US airline sentiment data set, which was extracted from Twitter. It contains an absolute mountain of tweets, both positive and negative, and neutral, relating to tweets about airlines. So here is our data set. And what we've done is we've imported each of the tweets. Again, remember, it's labeled. So what we've done is we've imported each of the tweets here together with a label. So 0 is neutral, 1 is positive, and 1 is negative, and 2 is positive. Sorry, let me rephrase that. So here's our data set. You can see that we imported around 14,000 tweets, and each one is labeled with a sentiment. So 0 is a negative sentiment. It's the way that the labeling system works. It's reasonably coarse-grained, but 0 is a negative sentiment, 1 is neutral, and 2 is a positive sentiment. So, and then we again trained the model and said, based on the tone of the language and the types of words, and even the punctuation used in the tweet, understand or determine, obviously, or file that with a particular sentiment score, and then use that to train. So what I did earlier is I went on Twitter. This is from May 17, so 2021. And I am going to copy this tweet. And if we read the tweet, it does read negative. Okay, the person is desperate. It's late at night. I've been on hold for an hour and a half. Help. So we can clearly see that this is going to be a negative tweet. Now, the reason we know that is because we're looking at it. Now, typically, you don't look at the data that you're going to put in and predict against because we can clearly know the answer here. So what we would normally be doing is this will be completely unattended and automated. So I'm going to paste the text in and we'll get the data out and we can see the predicted score will appear at the bottom. Now it hasn't actually changed, so it's actually 0. So the predicted score is 0, which means it's a negative sentiment. But what if I change the text and say, I love your airline, you have great service, and you're always on time. And we can predict that. And of course, that is going to be a prediction of 2, which means it's going to be a positive sentiment. So it doesn't matter what I type, as long as it has that type of message, you can do that. Now, of course, this doesn't have to be of tweets. This can be of support conversations, chat logs, transcripts from your own call centers, that sort of thing can actually be done, and you can actually generate sentiment based off that. Now, our natural language API already has sentiment, but this is a further tweaking of that sentiment, specifically also to understand specific situations. Okay, all right, next one. This is again is another natural language API, this time on entity extraction. So entity extraction is what is something about, okay? Now, again, Google's natural language API can do entity extraction, but what you're seeing here is a particular data set that is actually to do with material science. So it has very dense words and difficult words, and words that our API default would just never be able to cope with. And so what we can do is we can take this very specific language and bring it into the natural language API and actually tweak it and tell the AutoML natural language API what it should be seen. And we actually have one of these already as a product for medical terminology because of the medical terminology itself is very difficult. So what you can see, we've taken a number of words and we've labeled them in different ways. So we've said there's some sort of method. This is the type of method. Here is a material. The green is a material. We've labeled something as a characterization. It's an application. So we've said each sentence contains these different properties. And we, again, loaded quite a few of those. And then, again, the model is trained now. And now, giving a sentence we haven't seen before, we can actually tell the model to actually identify what is in that thing and identify the different parts of the sentence. So we do have our prediction screen, and what I'm going to do is what we want to look out for if we go back. I'm going to write a random sentence that tries and puts all of this data together, so we can see words like material, application, sample, and things like that. So I'm going to try and construct a sentence that that does that. So the material might be iron. The word might be, let's do rusty. I'm not quite sure if you'll pick that up, but we'll give it a go. And what might we use it for? We might use it to create some sort of lining of a car wheel, okay? So we'll do wheel arch, maybe. Okay, so let's give that a go. So we'll now turn this into a sentence. So ferrous iron, we'll use it, get rid of that, can be smelted and modified for use in vehicle wheel arches. Oops, sorry, wrong key. Okay, so I have no idea how this is going to turn out. So we're going to we'll both be surprised together. So let's predict and see what we get. Okay, it's actually done a pretty good job. I think I did okay. So the first thing it did is it turned up a material, which is ferrous iron. That is exactly correct. What was the method? Well, we smelted it. That's also correct. And what is its application? Well, we were using it in vehicle wheel arches. So actually, for a bunch of random words, I thought I did pretty well, and I thought the AutoML model did pretty well as well. So I'm actually pretty happy with that. Okay, so again, if you're dealing with domain-specific information, entity extraction is really, really good. And of course, you can then run lots of interesting analysis on this data as you go. So, a single thing like this is not perhaps very interesting in isolation, but if you run this across a whole corpus of text and then run the analysis, you can then start to do things like counts. So how many times does the word ferrous iron appear? And how many times does it appear in proximity to vehicle wheel arches and things like that? So it's also not just about identifying the entities in the text, but also the relationship between those entities as well. Okay, 2 more demos to go. So thank you for sticking with me. Okay, so the last 2 demos are on video. So you can think of so many use cases for video, it's crazy. So from surveillance cameras to video snippets for sports, as you can see here, to lots and lots of different uses. You can literally do anything, right? So, and also don't forget that we do have the Video Intelligence API, which is also very rich in terms of what it's capable of understanding, particularly with things like colors, locations, objects, shot changes, and things like that. And you can even extract the audio transcript from the video as well. All right, now this also is a little bit different because all of the previous demos we've seen have had thousands or tens of thousands of samples. But what we've done here is that we've only trained our model on 100 items each. So what we've said is, based on the video, try and identify the type of activity in the video. And so we've only had to supply 100 examples per type. And so the type is somebody doing a cartwheel, somebody playing golf. I don't know why they labeled it kickball, but it's actually soccer or football. A pull-up, which is exercise, or riding a horse. And so what happens is that the AutoML will pick apart all of the frames, inspect what's inside the frames, and again build that model for us to allow us to make predictions. So let's take a quick look. Now this one, because it's video, we have to do things a little bit differently. So I'm just going to paste in some text here. So what we need to do is pass in, we can do bulk predictions. So we're passing in a bulk lot of data, and we need to send the output somewhere else. So I'm sending it to this folder. And then what we can do is run and get the predictions. Now this takes a few minutes to run, and the time it takes to run is a function of both the resolution and the length of the video. So I'm not going to make you sit around and for a couple of minutes to watch it do its thing. So just like a good cooking show, here is one I prepared earlier, using the exact same data set, using the exact same video and everything. So this is a clip of some soccer. So now what we're seeing is a football game. We'll play it. And once the video starts to run, we can actually start to see the confidence of how confident this particular model is in the fact that are they indeed playing soccer or football or whatever you prefer to call it, or as this person, as you know, called a kickball. So we can actually see the incidences here across different times. And in this case, we can also analyze different parts of the video. So here we're analyzing the individual shots. Now this is mostly a single shot clip, but there's another clip, so we can analyze across individual shots, we can analyze across the entire segment, or we can analyze in 1 second intervals. So if you have a movie, it depends, again, the use case you might use depends very much on how the type of video that you're going to be processing. So the use case may be different. So here is it's not doing a great job of predicting in this particular case, but this is just a random video I pulled off the internet of people playing football. So I don't know the quality of data that was put in. Typically, of course, you'd have a lot more control about the data that was used. Why did the guy come out of the goal? Sorry. Anyway, you have a lot more impact and a lot more control over, the data that was coming in and the data that you're predicting against, rather than just me pulling random videos off the internet. All right. Okay, so lucky last again is another video use case, this time with rugby. So this one is to do with object detection. So that is what we did in the last one, is we said, what is this video about? Is it about somebody playing football? Is it about somebody playing, doing cartwheels or riding a horse or playing golf? But you can also say, well, what is actually going on in the video itself, right? Can we identify objects in the video? So that is where AutoML object detection comes in. Very similar use case. We labeled the images, except in this case, we labeled the people in the image, right? In this case, that's a rugby game. And we can then predict, we can then feed it a video and say, identify people playing this particular sport and where they are on the field. And because we can then identify the objects, we can trace that person, in this particular case in the rugby game, we can trace that person over time, right? So we now get a positional temporal combination in our video. So maybe not so relevant for sport, but if you think about it from a surveillance point of view, if you have like surveillance footage, you can identify, you can train the model to learn about your cat coming into the front. You can train the model to detect people in the surveillance camera, and if it detects a person, it will raise an alert. A really interesting use case of somebody doing something like this with their pet cat, with a cat door. And he trained a model to know the difference between his cat and his cat who had caught a bird. And because he didn't want the cat coming inside and dumping the dead bird on his floor. So what he did is he hooked up a camera to his cat door. And if the model detected that the cat had a bird in its mouth, it would actually lock the cat door and prevent the bird from getting in. If the cat obviously was just coming in as this everyday thing and didn't have a bird in the mouth, the machine learning model understood that too and would let the cat come and go as it's pleased. And I thought that was a really cool use case of machine learning to avoid stepping on dead birds on your carpet. Anyway, so back to the rugby. So I'm going to, here we can see the predictions again. So back onto cloud storage, and just like last time, I'm going to view the previous one that I prepared earlier. And so here is the video of our rugby players, and each of these orange squares is a rugby player, and we can actually watch them move around. Now, as I said, remember, AutoML is not always perfect, and so here you can see some situations where we are missing rugby players. But again, we can tweak the confidence up and down and have it do a slightly better job of detecting the players. So here I've said with a 25% confidence, it's pretty much getting everybody all the time. Again, so you would tweak these for your specific use case. And you can actually see all of the different, this orange bar down here is just a visualization that shows where everybody shows up. Okay, and you can actually see we've also how many rugby players we're counting at the time. So you could also think about this for vehicles, right? So on the NLEX or SLEX or what have you, you could actually do use machine learning to do a vehicle count of the number of vehicles waiting at the toll gates, for example, as a measurement of like traffic density or something like that. So, and we're going to talk a little bit about that in a separate presentation following this one. Okay, So that is all of the demos. So quite a lot to get in there. So just to recap, we saw a natural language demo, determining the genre from a movie plot line. We had a vision demo around image classification, so it was pneumonia versus normal. We did object detection, detecting planes and satellite imagery. We did another one of looking at documents to determine, find different parts of the document page. We did an Automl tables to predict Titanic. We did the Translate API from English to Spanish, from Spanish to English. We did sentiment analysis based on tweets from airline passengers. We did entity extraction from a set of documents about metallurgy and metal science. And I did that interesting one about doing iron and using it in car tires. And then finally, we did these last two video demos, one of determining what kind of sport is being played, and also this one here looking for objects in a video clip itself. All right, so the last thing I want to cover is not a demo, just a few more slides where I want to talk about MLKit. So MLKit is is part of Firebase, and it's a way to deploy machine learning models onto a mobile device. That is a mobile phone. So it brings all of Google's ML right into one consistent SDK that you can then put, address on the user's device. Now, these models are optimized for mobile. We have a whole bunch of models out of the box, but the super cool thing is that you can deploy custom models. So not only do we have base models, and you'll see those in a moment, we also understand AutoML models. So you can deploy all of the AutoML models we've seen can actually be deployed on a mobile device and have things done on the mobile device inside your application. Not only that, but we can also deploy custom models. So if you've gone to all of the effort of creating a custom model, so for example, with image detection, you can then deploy that model onto the device and we will run it for you. A good example of this was a promotion we did in New Zealand. So for those of you who don't know, I'm from New Zealand, and New Zealand has three official languages. So we have New Zealand Sign Language, we have English, and we have Maori. Maori is the language spoken by the Indigenous people of New Zealand. So what we did one year is we used MLKit and we associated Maori words with objects. So somebody could use the app to take a photo of an object, and then we would use MLKit, the model that we deployed, onto the phone to show the Maori word associated with that object. So we didn't use Vision API and then to give us the English word and then go from English to Maori. We went straight from the object to the Maori word right on the phone using a custom machine image detection model. So very, very exciting and very, very cool. And you can think there are so many possibilities for this. Let's take a look at some of the base models that we have. So straight out of the box, we can do text recognition, image labeling, barcode scanning, very cool, face detection, and we can actually do some stuff around selfie detection as well, landmark recognition, object detection and tracking, pose detection. I think that's really interesting. Like for those of you who remember Xbox Connects, there used to be all these exercise games or you would hold different poses and the Kinect could determine what you were, where you were standing and how you were standing. Well, we can do that on mobile devices now, right? Translation. So we've talked a fair bit about translation. One of my favorite features, Smart Reply. So we will actually, if any of you have an Android phone and use Gmail and text messages and so on and so forth, you know how Smart Reply works. We will look at the content of the message and predict what is the ideal reply for you to shorten your reply time. Well, you can bake this into your own applications today. And finally, as I've mentioned, AutoML. So you can take all the AutoML stuff that we've talked about and deploy it straight onto the device. So if you want to learn more about ML Kit, you can go to this URL, developers.google.com/ML-kit, and read all about it. All right, well, that brings us to the end of the presentation. I just want to thank you for hanging in there and listening. And I do appreciate the time that you've spent with me. And I hope looking at all of these AutoML demos gives you an idea and some inspiration of the type of AutoML that you can build for yourself and realize how easy it is to get started with machine learning. Thanks, everyone.
Now comes the fun part. We want to help you build real-world services using Google Cloud's technologies. To do that, we want to show you 5 cool examples where we take a concept across retail, smart homes, smart lifestyle, and IoT solutions and build it out using different cloud services. Hopefully, this will help inspire you to bring your own ideas to life on Google Cloud.
Software developers, we're not known for our rockin' style, are we? Or are we? Today I'll show you how I used ML to make me trendier, taking inspiration from influencers. I'm gonna build an app that analyzes my closet and pictures of fashionable influencers and then makes me outfit recommendations. If I'm missing an important piece, it'll also recommend me products to buy. Let me show you how. So the way this is going to work is that I'm going to grab a bunch of fashionable inspiration pictures from social media, and then I'll take a bunch of pictures of my wardrobe, and I'll try to match the pieces that I already own to those fashion pictures using machine learning, which will help me put together outfits. I'll wrap this whole thing in a Firebase app so that I can scroll through outfit recommendations on my phone. All right, let's build this thing. So first, I needed to catalog my entire wardrobe. So I thought I could just grab a few pictures of me wearing clothing in everyday life and then use computer vision to pick out the items. To do this, I used a feature of the Google Cloud Vision API called Object Detection, which identifies objects in photos and then draws a little bounding box around them. As you can see, it kind of worked. It identified my top, shorts, shoes, stuff like that. But since I'm going to be matching my clothing pictures to inspiration pictures, I realized that the quality of my pictures had to be really high. They couldn't be at weird lighting angles or anything like that. So I accepted the sad fate that I was just going to have to take a picture of every single item in my closet, which I did painstakingly over a couple of days, dressing and undressing my mannequin and taking pictures of all my different shoes. Next, I needed to find some people who actually knew something about looking trendy and bonus points if they also worked in tech. So I reached out to Laura Medaglia. Laura is a developer who posts lots of fashionable outfit pics of herself on Instagram, where she's at CoderGirl, and from head to toe, which is important because we need to capture those shoes. With her permission, I downloaded a bunch of her pictures and uploaded them to cloud storage. Again, the goal here is to take a bunch of Laura's pictures and then pictures from my own closet and see which of her outfits I can kind of recreate. Now, challenge one was that not all of Laura's pictures are actually of clothing, so first I had to eliminate those and select only the ones where she's in an outfit. For that, I used a feature of the Vision API that does image classification. This feature returns a bunch of tags describing what in general is going on in an image, and one of the tags it returns is fashion. So I sorted through all of Laura's pictures and only kept ones that had a person in them and that were also labeled fashion. And with that, I had my inspiration image dataset. Now, the next step is to implement the feature that looks at my closet and the inspiration picture and matches them. For that, I'm going to use yet another feature of the Google Vision API called Product Search. If you're ever scrolling through a store and you're looking at a product and you see similar items, that's the functionality that the Google Vision Product Search feature gives you. So the next step is to create a product set. For this, you'll want to use the PyVision Product Search library. The first step is to create a product search client that connects to the Google Cloud backend. And next, you'll create a product set where you can hold all of your clothing items. I called mine Dale's Closet. Next, you'll want to go to the spot where all of your clothing items are stored. As you can see, I've got all of mine in a directory. And if I want to add something like this black bomber jacket, in the code, I create a new product, I name it, I give it the category apparel, and then I add any labels that I might want to later go back and filter by, so just show me jackets. And then the next step is to teach the model what this bomber jacket looks like. And for that, you want to add paths to all of the different files as reference images. It's better if you can take pictures from different angles with different lighting conditions because it will help the model generalize better. Now, to make this a little bit easier for you, I wrote a script in Python so that if you organize your images into a directory structure, then you can just run this script and it will automatically create a product set for you. Make sure you check out the blog post to see how. Once you're done creating your product set, it'll take about 30 minutes for the API to actually index those images, so just hang tight. When it's finished, we get to actually make outfits with ML. To do that, we'll call the search function on the product search API and pass it a path to an image file. First, it analyzes that image and identifies any clothing it finds, then it looks through your closet and finds the best matches. And now here's where it gets interesting, because even though the API returns back similar items, what we really want are outfit recommendations. An outfit like has only one pair of shoes, and you can't be wearing a skirt and pants at the same time, probably. So we need to do a little bit of finagling. And that's kind of par for the course with ML models. They usually don't give you back exactly what you want, so you have to use your expertise and domain knowledge to make sure that the predictions make sense. So I'm gonna roll my own outfit algorithm that defines rules for what pieces of clothing can be in an outfit. And we'll take all of the confidence scores returned by the API and generate one new quality score for the entire outfit. I did all of my outfit making logic in a Python script which wrote out all of my outfit recommendations to Firestore. Then I built a little front-end app that pulls in all the recommendations sorted in score order. Let's take a look at how it did. If you want all the details on how I built this app, make sure you check out the blog post linked below. And follow Coder Girl on Instagram to get your own neat techie outfit inspo. See you next time.
Wouldn't it be nice to add locally running AI to your appliances and control them with just your voice without needing any internet connection? Switch off. Switch on. Let's build this today. We have a delivery. Let's see what this could be. It's the new Coral DevBoard Mini. Let's unbox this one. The DevBoard Mini is a single-board computer for prototyping locally running AI and ML. It's a lot smaller than the Coral DevBoard and only a little bit bigger than the Coral USB accelerator. But where the USB accelerator needs a host computer, the Mini is a fully featured board running Mendel OS, which is a derivative of Debian Linux. The board has a quad-core ARM CPU, 2 GB of RAM, Wi-Fi 5 and Bluetooth 5. There's a 3.5mm headphone and mic combo jack, a speaker output terminal, camera and display connectors, a micro HDMI port, and 2 USB-C ports, both of which can be used to power the board. And then of course we have the Edge TPU machine learning accelerator, which runs at 4 trillion operations per second, executing for example the MobileNet V2 model at almost 400 frames per second. And the board has a built-in microphone, so we can use this microphone to record our voice and run a voice classification machine learning model to detect what we are saying and then control other appliances. But how would such an Edge AI architecture look like? Well, we wish to say some key phrases such as switch on to control our home appliances. Our voice is recorded by the onboard microphone. Then we pass the recording to the Edge TPU, which runs a key phrase classification machine learning model. We get the detected key phrases and execute actions based on those. The action can be to send an API call to our equipment. In this scenario, I'm using a light and a smart power switch, both of which have a control API. Okay, let's build this. First, we need to power on the board. And then we connect to the board using MDT shell. And the first thing we could do is to download the Google Coral example project for detecting audio key phrases. So what I can do is git clone the repository here. And let's take a look at that. The pre-trained model can recognize around 140 key phrases. So what we can do is we can go to the list and pick and choose keywords that we need. For example, we want to switch on and switch off the lights. And the key light also supports turning up and down the brightness, so we can use those keywords. And the default brightness for my key light is actually 11%. So why don't we use the key phrase position 11 to go back to that default brightness? We can test the keyword inference with this example application. It will record your voice, pass it through the Edge TPU, running the pre-trained model. Let's try with the keywords we selected. Position 11, switch on, switch off. Okay, that works. Now we need a way to control our lights programmatically. Let's start with the Elgato key light. There's a Python module called leg light, so this should work for us. Let's first install it with pip. Alright, and now let's try it. Import leg light. And then we make a leg light object. And we execute elgato.off. Alright, that worked. Let's switch it back on. Then for my lights in the background, I need to use a mechanical power switch. So let's try using this smart switch, which has Wi-Fi and a Python client as well. So let's now try sending a Python call to the switch, and my Edison lamp is connected to that. Alright, that works. And let's switch it off. Great. So, we can control the lights with API calls, and we can detect our keywords. Now let's bring these two together. To do that, I've extended the Coral example and implemented a callback function. It's a very simple callback function. It will simply execute an operating system command based on the command that we received. And the mapping between the keywords and the shell commands to execute are in a config file. So you don't need to change your code. You can simply configure here what command you want to execute based on the keyword that was detected. So let's try this by executing this script manually first. So we execute the light control script and we tell it to increase the brightness. Okay, that seems to work. And let's bring it back down to the default brightness. And now it's time for the big test. Can we use our voice to control our appliances in the house? So let's start this app on the Coral DevBoard Mini and say our keywords. Switch off, switch on, turn up, turn down, position 11. Alright, well that's all for this episode. I really hope that you enjoyed this first look at the Google Coral DevBoard Mini. Switch off. The holiday season. Too many yummies. I need to check something. I knew it! My exercise to yummies ratio has gone critical. I need a New Year's resolution. I need to exercise more. But I shouldn't just exercise more, I should exercise better. It's really important to have a good form when exercising to avoid any injuries. I really enjoyed Dale's episode earlier where she used the Video Intelligence API with Zach to analyze football kicks and her tennis form. But that requires you to upload the video of your exercise. Maybe you are at a remote training location like a mountain or a beach where you don't have any internet connection. So why don't we try to build an Edge AI sports analyzer that works fully offline? Let's call it AI Coach. So how could we build it? Well, we can run the app on our laptop and offload the machine learning inference processing to the Coral USB accelerator. Then we need a machine learning model that we can use to analyze our form. In my earlier episode AI Director, I used a PostNet model that can detect key body features like eyes, ears and nose. So if we modify that app a little bit, we can then draw lines between the detected body joints. And finally, we need to film ourselves while we exercise. But we are now in social isolation mode, so we can't use a camera crew. And if we leave a static camera on the ground, we will just run past it because the camera cannot follow us. Aha, I have an idea. If we use a drone that has active tracking, the drone can follow us while we do sports and keep us in the frame. So that can be our film crew. Okay, let's do this. But first, we need to check where we can fly the drone. Oh no, all of Tokyo is red. It's a no-fly zone. Hang on, what is this? Izu Peninsula. That's it. That's where we need to go. Welcome to the AI Coach Testing Center, TARP. We are here to collect training data of different sports using the film crew. So, let's first launch the film crew and start collecting our data. Okay, film crew is ready in the sky. Our first sport is running. Let's go.
Sport 1. Running. Go.
Okay, I think we have enough data for running. Let's do some other sport next. Let's go kayaking next. Hang on, something is missing. We need a kayak.
Sport 2. Kayaking. Go.
Okay, time to cool down a bit. Time for the last sport, which is swimming.
Sport 3. Swimming. Go.
Oh, that was refreshing. But I think film crew lost us there in the water a little bit, but never mind. I think we have good enough footage from the other spots. So that's it from Izu. Back to the studio. Okay, now let's analyze our training footage. Okay, looks good. Now let's connect the Coral USB accelerator and run the exercise videos through our pose analyzer. Let's start with swimming. Okay, it kind of works. It can actually detect our body joints when we are near the surface, but it loses us when we go underwater. So we can't really use this. How about kayaking? Okay, much better. So with this one, we can actually start looking at my posture and how far front or back I pull the paddle. Then how about running? Okay, this one is the best one. We have all the major body points detected. One important thing about running is that we should avoid overstriding, where the foot lands in front of the body. That can cause big impacts on your joints, and it's actually breaking our movement. So let's try to use this stick figure to estimate if I'm overstriding. But there's an issue. The drone was filming me from the side, exactly from the side. So it's kind of hard to see where my foot lands. Is it in front of my body or not? Because there's an angle.
Oh, hey Markku, how's it going?
Oh, hey Dale. I'm struggling with the orientation. Sometimes the drone wasn't really filming me from the side.
That sounds really tricky. I think maybe what I would do is, rather than try to understand every different orientation of you running, why don't you use the PoseNet model to just tell if you're in a good orientation, like if you're 90 degrees to the camera, and maybe you can just throw out the frames that are more complicated.
Oh hey, that's a... Thanks, I'll give it a shot.
Yeah, no problem. Enjoy your private beach. See ya.
See you.
So Dale gave me a great idea. Let me make a function that ignores video frames where the angle was at an offset, and only keeps and analyzes the overstriding from those video frames where the filming angle was good. Alright, now let's try this again using the new function. And there we have it. It works. And unfortunately it looks like I am overstriding. Well, at least now I know. So I need to fix that next time I run. Well, that's all for this week's episode. I really hope that you enjoyed it, and I hope to see you next time. Until then, bye bye. In this episode, I will show you how to build an asset tracking solution. It will be handy if you need to track your shipments, your vehicle fleets, your heavy machinery, livestock, or maybe pets. Or not cats. I know where the cat is. He's right there. So what do we need to build? Well, first we need a device that is small, easy to maintain and low power, so it can run on batteries. Then we need good network coverage so that the device can read sensor readings and send the data out when necessary. Then we need to know where the device is, so we need a positioning system. And finally, we need a backend system to analyze the data in real time and let us visualize the data, for example in maps. First we need LP1, a low power wide area network. Let's use Sigfox for that. And then we can use the Sigfox Google Cloud Platform integration so that when the devices send data, it's received by the Sigfox network and it's forwarded in real time to Google Cloud. And then in Google Cloud we have a stateless event-driven backend system that streams the data in real time to the data warehouse. And then in BigQuery we can execute GIS or Geographical Information System queries against the data. Then we need the device. It should just work with minimal maintenance. So let's use the PyCam globeph. It's an ESP32 microcontroller which has multiple radios: Wi-Fi, Bluetooth, LoRa and Sigfox. The PyCam board consumes only 35 mA during idling and 91 mA during Sigfox transmission, but then only 18.5 microamps during deep sleep. So what we can do is have the board wake up at regular intervals, read the sensor values, transmit those with Sigfox and go back to deep sleep. This way, the board's battery should last several months. Then we need to know its position. So let's use the PyTrack sensor shield. The sensor shield provides a 3-axis accelerometer, so you know, for example, if your package is suddenly upside down, or if there's some heavy impact that may have caused damage. And then for positioning, the shield has 4 satellite receivers. Now let's take a quick look at the device configuration. The client code is written in MicroPython, and one of the things that the device does is try to get a GPS lock when it wakes up. So it will try to get an accurate position. And then it will also read the accelerometer values as well as the battery voltage. And all this information we want to send up to the cloud. So we need to pack these sensor readings and the GPS coordinates into just 12 bytes, which is the maximum payload size in Sigfox. Then we will send, using the Sigfox radio, these 12 bytes. And then depending on the configuration, the device will either go to normal sleep, which is in development and testing mode, or deep sleep, which is for production systems for preserving battery power. So now let's connect the device and see what happens. Okay, the device is booting up, it's connected. It will try to get the GPS lock. It did, we have the coordinates here, as well as the sensor readings and the battery voltage. And now it's sending these 12 bytes data payload over the Sigfox radio. So what I can do is I can copy this hexadecimal 12 bytes binary string to the clipboard, and in the terminal here we will use a utility which is part of this open source solution to parse or decode these binary messages. So we can see here that the device sent indeed the coordinates, the accelerometer values, and the battery voltage. So what happens in the network side? Well, first, the Sigfox platform receives the message, and here we have configured in the account the callbacks. So the Sigfox network will use this callback configuration to forward the data in real time from the devices to Google Cloud. In this case, to these cloud functions. So we have cloud functions receiving the data, parsing it using the decoding function you saw earlier. We have service messages reception, as well as streaming the received data to BigQuery, the data warehouse. So here in BigQuery, we can see example rows of data received from the Sigfox devices. We have the device ID, the binary data payload, the original, as well as the parsed, opened, normal payload, if you will. You can see coordinates here, the accelerometer values, voltage, network reception quality level, the local Sigfox operator, as well as the Sigfox Atlas estimated coordinates. So now in the data warehouse, we have both the estimated coordinates as fallback, as well as the satellite coordinates when those were received. So now what we can do is have actionable insights, as well as visualize this data using GIS, Geographical Information functions, in BigQuery. Let's do that next. Let's run a GIS SQL query that shows the last 4 table rows data in maps. Alright, looks good. The points are near the office. Okay, so functionally it seems to be working. But we really should do a real-life asset tracking test. So we need something to track. Well, how about this one? Let's bring this along. And let's go. Okay, I think that should do it. Back to the studio. All in the name of data science. All right, now let's see. Do we have any new asset tracking data? Let me refresh BigQuery. Yes, we do. There's a lot of new rows. That's promising. Now let's go to the visualizer. And let me refresh this query. Boom, there we go. That's the route. It worked. Whew. If you want to try this asset tracking solution yourself, we have fully open sourced it together with my colleague and good friend Marco. Marco, say hi.
Ciao a tutti.
So please see the link down below in the description to download the tutorial and all the source code. And as always, if you like it, please click the like button, click subscribe and leave a comment below. And see you next time. Bye bye.
Before you can make a loaf of sourdough bread, you need to make a sourdough.
I ordered some ice cream.
This is
Yay.
a culture of flour and water. Enzymes in the flour also
Is the
start
ice
to
cream
break down
alright?
starches
I don't
into
know.
simpler sugars.
I will go check. There's something here. Oh no, it has melted. We need to fix this. So we often get deliveries, but we don't know about it. How could we fix this?
Pushes notifications about these events to my mobile phone or chat app.
I think I will be using it myself. Ah, I got it. Okay. So I need to send notifications to Google Chat and those go to my phone. But how do I know when the delivery box has been opened? We need something that notices when the door opens and closes. There's no electricity, so it has to be battery powered, hopefully for months. If it rains, it should be waterproof. And there's no Wi-Fi network there, so we need some other type of connectivity. Let's see what we got here. Nope. Nope. All right, I think this should do it. We can attach the Sensit device to the delivery box, and it can notice if the door opens or closes, and transmit a message using Sigfox radio. Then we can configure Sigfox to forward the data to Google Cloud, where we have cloud functions receiving, parsing, and analyzing the data. And if the payload says that the door was opened or closed, we can call a webhook which is pointing to a Google chat room. And then on our phone we can get a notification from Google Chat saying that we have gotten a delivery. In the magnet mode, the device will transmit a message if it detects a magnet nearby. Here in the Sigfox backend we can see the message sent by the device. There we go. And then it will transmit another message if the magnet goes away. And here's the second message when the magnet went away. Let's now investigate these weird binary hexadecimal payloads sent by the device. To do that, we can use an open source utility that is part of the solution that I published earlier for using Sigfox Sensit with Google Cloud. The utility lets you parse or decode these binary messages. So here we can see the device battery voltage. The mode is 5, which means the magnet mode. And there was an event, magnet status 0, which signifies that the magnet was there, but then it went away. So for example, the door opened. And if we decode the other message when we were testing, we can see that the magnet status was 1, which is the second type of event when a magnet came near the device. So this way we will be able to determine if a door opens or closes in the delivery box. Next, let's forward the data to Google Cloud. For that, we can use the Sigfox Google Cloud integration that I open sourced earlier. By the way, all the links to these solutions are down below in the description. So here we can see that we are able to receive data from the devices, but we need to forward it to a backend system like Google Cloud. For that, we can use callbacks. Currently, you can see I don't have any callbacks configured. To configure those callbacks easily, we can use the integration. And now we can first check using the APIs, do we have any callbacks configured? No, you can see 0 callbacks configured. So let's now use the same integration script to create programmatically all the 5 callbacks that we need for Google Cloud integration. So the script says that it has created 5 callbacks, and indeed you can see them here. They are pointing to cloud functions. We will use cloud functions for receiving the data from the callbacks. But in my account, I don't have any cloud functions running. To fix that problem, we can deploy 2 cloud functions that are part of the integration that will handle the data and service messages reception. So let's first deploy the callback data cloud function. This one is responsible for receiving the data messages from the devices. So now we can see that this first cloud function is being deployed. Okay, the callback data cloud function has been deployed, and I will then start deploying the second one, which is receiving the service messages. We can now test the first function with the magnet. So let's put the magnet near the device again, which should trigger sending another payload. And now, since we have callbacks configured in the Sigfox backend, they should be forwarding the data message, in this case to the callback data function. So let's click the function, and then we can go to the logs and take a look what has happened recently. Okay, something has happened. Somebody has executed the function. So we have received a Sigfox message. You can see the binary payload here. And then the next message in the log says that we have published this message data payload as is to Cloud PubSub. I should also start deploying the service messages cloud function. Let's wait for that to complete. While the service messages handling function is being deployed, we can figure out what to do with the data that's going to PubSub now. So we will need one more function. So I've made a function that is reading the data from the PubSub message queue, and then it is parsing these binary data payloads, and then it investigates the payload. And if there is a magnet status event there, that will then trigger a function in this cloud function that is sending a webhook message. So next what we want to do is to have a Google chat room and then configure a webhook API for that. So let's now go to Google Chat and create a new room. And we will call it building. There, now we have a new room. And now in this new room, what I want to do is to manage the webhooks. So let's create a new webhook that is called delivery box. We click save, and now we get a URL. This is now the URL that we can use to post messages from the delivery box bot to this Google chat room. So what we can do is we copy the webhook URL, we go to the configuration file for this third cloud function, and we save the config file. So now for this new cloud function that is parsing the payload, investigating if the door has been opened or closed, it knows which webhook URL to use to post a message to Google Chat. So let's deploy now also this cloud function. So we'll execute gcloud functions deploy for this push webhook function. And you can see that it will be triggered by the pops up topic Sigfox data. So this function will be triggered by the data payloads put there by the first cloud function, callback data. Okay, the webhook function has just finished deploying. And if we go back to the cloud functions page here, let's refresh it. Now we have all three cloud functions that we need. Just to recap, callback data receives data payloads from Sigfox, drops them in a pops up message queue. Callback service receives control plane messages, events happening in the Sigfox network, and then push webhook cloud function parses the Sigfox sensitive data payload, and if it contains a door open or close message, it should push a new message to our chat room. So let's now test this by removing the magnet from near the device. Okay, I took the magnet away. That should be a door open event. We are in our chat room. And let's see if this works end to end. Here we go. We got a new message, delivery box open. Let's go install the device on the delivery box.
Proofing baskets support the shaped loaves
I
during
ordered
their
some
final
more ice
rise
cream.
before baking.
Yay!
Ice cream!
Get it. Get it. Yeah.